Alright, we're going to pick up with Chapter 3, which covers the relational database model in more depth. In this chapter you will learn that the relational database model offers a logical view of data. You'll learn about the relational model's basic component, which is relations. That relations are logical constructs composed of rows, which is tuples, and columns, which is your attributes. In Access, they're called fields and records. Your fields equate to attributes, and your records is your rows or your tuples. That relations are implemented as tables in a relational DBMS. You'll learn about relational database operators, the data dictionary, and the system catalog, how data redundancy is handled in the relational database model, and why indexing is important. So in Chapter 1, you learn that a database stores and manages both data and metadata. You also learn that the DBMS manages and controls access to the data and the database structure. Such an arrangement, placing the DBMS between the application and the database, eliminates most of the file system's inherent limitations. The result of such flexibility, however, is a far more complex physical structure. In fact, the database structures required by both the hierarchical and the network database models often become complicated enough to diminish efficient database design. The relational data model changed all of that by allowing the designer to focus on the logical representation of the data and its relationships, rather than on the physical storage details. To use an automotive analogy, the relational database uses an automatic transmission to relieve you of the need to manipulate clutch pedals and gear shifts. In short, the relational model enables you to view data logically rather than physically. The practical significance of taking the logical view is that it serves as a reminder of the simple file concept of data storage. Although the use of a table, quite unlike that of a file, has the advantage of structural and data independence, a table does resemble a file from a conceptual point of view. Because you can think of related records as being stored in independent tables, the relational database model is much easier to understand than the hierarchical and network models. Logical simplicity tends to yield simple and effective database design methodologies. Okay, so some characteristics of a relational table. A table is perceived as a two-dimensional structure that's composed of rows and columns. Each table or row is called a tuple and represents a single entity occurrence within the entity set. Each table column represents an attribute, and each column has a distinct name. Each intersection of a row and column represents a single data value. All values in a column must conform to the same data format or data type. Each column has a specific range of values known as the attribute domain. The order of the rows and columns is immaterial to the DBMS, and each table must have an attribute or combination of attributes that uniquely identifies each row. Okay, keys consist of one or more attributes that determine other attributes. And they're used to ensure that each row in a table is uniquely identifiable, establish relationships among tables, and ensure the integrity of the data. Alright, a primary key is an attribute or combination of attributes that uniquely identifies any given row. In the relational model, keys are important because they are used to ensure that each row in a table is uniquely identifiable. They are also used to establish relationships among tables and to ensure your integrity of your data. I want to stress these points. Keys are important. A key consists of one or more attributes that determines other attributes. For example, an invoice number identifies all the invoice attributes such as the invoice date and the customer name. One type of key is the primary key, and again, it's the attribute or combination of attributes that uniquely identifies a given tuple, row, record. Okay? The role of a key is based on the concept of determination. Determination is the state in which knowing the value of one attribute makes it possible to determine the value of another. Alright, if a relationship is has functional dependence, it means that the value of one or more attributes determines the value of one or more other attributes. In functional dependency, the attribute whose value determines another is called the determinant or the key. The attribute whose value is determined by the other attribute is called the dependent. And a full functional dependent is used to refer to functional dependencies in which the entire collection of attributes in the determinant is necessary for the relationship. Alright. We just talked about functional dependence and full functional dependence. Okay, a composite key is a key that is composed of more than one attribute. Key attribute is an attribute that is part of a key. Okay, what that means is there's an example in your book on page 75 that you might want to look at. You have your student number and your student GPA. And then in the first functional dependency, student num is an example of a key composed of only one key attribute. In the second functional dependency, student last name, student first name, student initial, student phone is a composite key composed of 4 key attributes. Okay. It talks about entity integrity. It is a condition in which each row in the table has its own unique identifier, which is the primary key. All primary keys cannot be duped. They must be unique, and they can never be null. Null means that there's an absence of any data present. An unknown attribute value, a known but missing attribute value, an inapplicable condition. All of that would result in a null, and you cannot have a null in your primary key. Referential integrity. Foreign keys are used to ensure referential integrity, and that is a condition in which every reference to an entity instance by another entity instance is valid. In other words, every foreign key entry must either be null or a valid value in the primary key of a related table. Alright, a super key is an attribute or combination of attributes that uniquely identifies each row in a table. A candidate is a minimal super key, a super key that does not contain a subset of attributes that is itself a super key. Your primary key is a candidate key selected to uniquely identify all other attribute values in any given row, and it cannot contain nulls. A foreign key is an attribute or combination of attributes in one table whose values must either match the primary key in another table or be null. And your secondary key is an attribute or combination of attributes used strictly for data retrieval purposes. So let's look here at this example. You have your first table there, which is product, and you have your vendor table. Your primary key in your product table is your product code, and then you have some other attributes there: product description, product price, product on hand. Then you have your VIN code, which is a foreign key from another table. And if you look in your vendor table, VIN code is the primary key in that table. Then you have your VIN contact, your VIN area code, and your VIN phone number. There is no foreign key in the vendor table, but if you'll look at it, your primary keys have to be unique in both tables. Your product codes and your VIN codes cannot be duped. However, if you look at VIN code in your product table where it is the foreign key, it can be duplicated. Different products can be vended by the same vendor. Okay, so integrity rules. Entity integrity requirement. All primary key entries are unique and no part of a primary key can be left null. The purpose, each row will have a unique identifier and foreign key values can properly reference back to the correct table and the correct record that matches that key. An example, no invoice can have a duplicate number, nor can it be null. Integrity rules, if we keep going, a requirement, a foreign key may have neither a null entry can have either a null entry or an entry that matches a primary key value in a table which is related to the table you're in. The purpose: it is possible for an attribute not to have a corresponding value, but it is impossible to have an invalid entry. It is impossible to delete rows in a table whose primary keys have mandatory matching foreign key values in another table. So if they're related, and if we go back to vendor, if it's related, you cannot delete record 232 from the vendor table as long as it's linking in record as a VIN code foreign key in the product table. If it matches records, if it's being used, you cannot delete it from your vendor table, because it would create foreign keys being used in your product table that did not exist in your vendor table, which would cause integrity problems. So it would not let you delete that record unless you changed your codes or left the codes null in the product table. An example: it's impossible to have invalid sales representative numbers. So here again, it does integrity rules. Your customer table has your customer code. Your agent code is your foreign key. It is your primary key in your agent table. You cannot delete the record for agent code 501 as long as it exists in your customer table as an agent code for a record in that table. You would have to either make it null or change it to a different agent code before it will let you delete the agent in the agent table. Alright. Flags. To avoid nulls, some designers use special codes known as flags to indicate the absence of some value. So if you looked at this table again, if you wanted to delete, let's say 502 in your agent table, you would have to go back in your customer table and give it some kind of code, say 99 for everybody that uses agent 502, so that they would know that agent no longer exists and there's not an agent assigned to those customers. Same thing here. If you wanted to delete vendor 232, you would have to give it a code of, say, 006. Maybe that's your error code. And then for the first and the fourth record, you would put in that 006 for your VIN code, and that will let them know that that product does not currently have a vendor. Okay? That's when the not null constraint is placed on a column to ensure that every row in the table has a value for that column. And the unique constraint is a restriction placed on a column to ensure that no dupe values exist for that column. That would be in your primary key mainly, that you cannot have a duplicate value. A theoretical way of manipulating table contents using relational operators is relational algebra. A couple concepts that comes with that. A rel var is a variable that holds a relation. For example, imagine you are writing a program and created a variable named qty for holding integer data. The variable qty for quantity is not an integer itself. It is a container for holding integers. Similarly, when you create a table, the table structure holds the table data. The structure is properly called a rel var, and the data in the structure would be a relation. The rel var is a container or variable for holding relational data, not the relation itself. Okay, the data in the table are a relation. And then the relational operators have the property of closure, and that is the use of the relational algebra operators on existing relations or tables, then produces new relations. Numerous operators have been defined. Some operators are fundamental, while others are convenient but can be derived using the fundamental operators. Okay, so select, also known as restrict, is referred to a unary operator because it is only used one table as input. It yields values for all rows found in the table that satisfy a given condition. Alright, select can be used to list all the rows, or it can yield only rows that match a specific criterion. So if we look here at select all will yield everything. If you select only price less than $2, it yields those two records. And if you select only P_code equals 311452, it yields that one product. Okay. Now project yields all values for selected attributes. It is also a unary operator, accepting only one table as input. Project will return only the attributes requested in the order in which they are requested. In other words, project yields a vertical subset of a table. Project will not limit the rows returned, so all rows of the specified attributes will be included in the result. So there's project. If you project price, it's going to give you the column price. It's going to yield them all. If you project P_description and price, you get all the product descriptions and prices. And if you yield a product code and price, it will yield all the product codes and their price. Okay, we move on to union. Union compiles all rows from two tables, excluding duplicate rows. To be used in the union, the tables must have the same attribute characteristics. In other words, the columns and domains must be compatible. When two or more tables share the same number of columns, and when their corresponding columns share the same or compatible domains, they are said to be union compatible. So if we look at a union, you have two different tables that have product codes, product descriptions, and price. Okay, and then if you do a union on them, it will yield a table that contains all of the information from both. But if you will notice, box fan is listed in the first table and the second table, so it's not shown twice, it's only shown once. So the second table only added microwave and dishwasher. And let's see, the next one is intersect. An intersect yields only the rows that appear in both tables. As with union, the tables must be union compatible to yield valid results. For example, you cannot use intersect if one of the attributes is numeric and one is character based. For the rows to be considered the same in both tables and appear in the result of the intersect, the entire row must be exact duplicates. Okay, if we look at intersect, you have student first name, student last name, and employee first name, employee last name. For an intersect, you are trying to find matching records, more or less. So if you run an intersect on these two tables, you will get a table that shows Franklin Johnson, because that is the only matching record where the first and last names match. Alright, moving on to a different relational operator, we have difference, which yields all rows in one table that are not found in the other table. That is, it subtracts one table from the other. As with union, the table must be union compatible to yield valid results. The effect of a difference operation, however, note that subtracting the first table from the second table is not the same as subtracting the second table from the first table. You wouldn't yield the same results. There's difference. Okay, so you've got your student first name and last name, employee first name and last name. If you subtract the employee table from the student table, you will get those 4 records because they do not exist. Let's see. Franklin Johnson is omitted from the first table because he exists in the employee table as well. And when you subtract that table, the other records don't have a match, so you still yield 4 records from the student table. If you had switched it and subtracted the student table from the employee table, you would have yielded 3 records: Franklin Lopez, William Turner, and Susan Rogers. Alright. Product yields all possible pairs of rows from 2 tables, also known as the Cartesian product. Therefore, if one table has 6 rows and the other table has 3, the product yields a list composed of 6 by 3 or 18 rows. Okay, so if we look here where you've created a product, you will see that product is noted by the multiplication symbol, and the product of the customer and agent relations will be written as customer with the multiplication x and agent. A Cartesian product produces a set of sequences in which every member of one set is paired with every member of another set. In terms of relations, this means that every tuple in one relation is paired with every tuple in the second relation. So you will see that you have product code, product description, price for flashlight, and it has added in the first one there the first row of the store aisle shelf, and then you have a second one that does that takes flashlight from the product and pairs it with the second row of store aisle shelf, and then you have a third record for flashlight which pairs it again with the third row of store aisle and shelf. So you have your product code, you have flashlight, you have the price, and then you have 23W5. And then your second one, you have the product code, flashlight, the price, and 24K and 9. And then you'll have the product code, flashlight, the price, and 25Z6. And then it will do that for every record in the product table. It will pair it with a row from the other table and give you a new record. So you will have 3 records based off of every product, adding store, aisle, and shelf in your new table that it creates. Okay. Now if we talk about a join allows information to be intelligently combined from 2 or more tables. Join is the real power behind the relational database, allowing the use of independent tables linked by common attributes. Okay, we look at a join. It's showing here your customer and agent tables. They're going to be used to show show a join. And it walks it through it in the book. I don't believe it's in the slides. No, I didn't think so. It walks you through these joins in the book. Let's actually look in your book on page 84 and let me help walk you through these. You have a natural join, which links tables by selecting only the rows with common values in their common attributes. A natural join is a result of a 3-stage process. First, a product of the tables is created. So you create a product of the tables like we did in the previous example. Second, a select is performed on the output of the product to yield only the rows for which the agent code values are equal. The common columns are referred to as the join columns. Okay. So then you would come up with the second figure there on page 85, where you have matched up your agent codes. And then a project is performed on the results of step 2 to yield a single copy of each attribute, thereby eliminating duplicate columns. So then it would do away with the duplicate agent code column and yield the table that is left there in the last picture there on the bottom of 85. And again, that is a natural join. Alright, and then it talks some more about an equal join, which links tables on the basis of an equality condition that compares specified columns of each table. A theta join, which is an extension of natural join, denoted by adding a theta subscript after the join symbol. You have an inner join, which only returns match records from the tables that are being joined. You have an outer join. Matched pairs are retained and unmatched values in the other table are left null. And then you have a left outer join, which yields all the rows in the first table, including those that do not have a matching value in the second. And you have a right outer join, which yields all the rows in the second table, including those that do not have matching values in the first. And in your book, there are figures that show you a left outer join and a right outer join, how it would look when it matches those agent codes and customer codes and all up on page 87, figure 314 and 315. Gives you an example of what it would yield in a left and right outer join. And I know some of this can be kind of confusing, so if you get confused on any of this, just send me an email, let me know, and I'll try to clarify it some more. Okay, a divide is an operation that uses one two-column table as the divided and one single-column table as the divisor. Okay, in your figure here that we're looking at, the divide contains the code and LOC columns. The single divisor contains the code column. The table must have a common column, in this case the code column. The output of the divide operation is a single column that contains all values from the second column of the dividend, which is LOC, that are associated with every row in the divisor. So the only common LOC for A and B is 5. So that's why it yields 5. Okay. Alright, now a data dictionary is another concept in working with relational databases. And it provides a detailed description of all tables in the database created by the user and designer